All right. Hello, everyone. Welcome to my talk. Today, I'm going to talk about implementing standard libraries. I'm going to share the design decisions, optimizations, and testing in Libc++. So Libc++ is a standard library implementation. It is the part of the LLVM project, and it is a standard library that ships with the compiler CLAN. So in today's talk, I'm going to share some interesting examples about optimizations in the library. I'm going to focus on some standard types like expected and also some algorithms. And in the end, I'm going to share some testing techniques we've been doing in the library. So the first example, So my name is Hui, and I'm a software developer at QRT, which is a hedge fund based in London. And I am a Libc++ contributor for the last couple of years, and I'm a member of the standard committee and the UK national body member, and I'm mostly working in the ranges study group, and sometimes I write C++ proposals. The first example I'm going to share is about stood expected. Stood expected is a utility class added in C++23, which is used for error handling. So the user can call a function that returns a stood expected, and then he can query the expected hash value or not, and also they can retrieve the value or the error out of the expected. Another question is, how do we implement this class in the standard library? And before we go into the details, let's first look at this example. Imagine we have a class foo, which contains an int, a char, and a bool. What is the size of this class? Any idea? Guess?
8.
Yes, that's right. So on most implementations, it will be 8 bytes, because we got a 4 byte for the int, 1 byte for the char, 1 byte for the bool. Then we have 2 bytes tail padding in the end. That's a typical implementation. Another question is, what should be the size of stood expected of foo and an error code?
16 question mark? Or 12?
Yeah, I think the answer is it depends on the implementation. Let's first look at the first implementation. So this is the implementation in GCC's libstood C++. Basically, we got a union, which contains either a value or an error. And then we have another Boolean afterwards to tell whether or not we got an error or got a value. So with this implementation, what will be the size? Right. Well, it's 12. So this is why. First we got the foo, we got the 4 bytes int and the char and the bool, got the foo's padding as well. Then the compiler puts the Boolean after the foo, right? And because of the alignment of the int, and the compiler has to put 3 bytes tail padding at the end. So that's 12 bytes in total. And now this is the implementation in Libc++, our implementation. It looks very similar. We got a union and a bool. And the only difference is that we apply this attribute, no unique address, in front of our members. And how does that make a difference? So no unique address attribute, the standard defines this way. Basically, it tells the compiler that our members are potentially overlapping. So what does that mean in concrete examples? So in this particular case, we still got the foo with the int and char and the bool. We still got 2 bytes padding for the foo. And because we tell the compiler that our members are potentially overlapping, what the compiler can do, it can put the Boolean hash value inside the tail padding of foo in this case. Right. So that makes our stood expected only 8 bytes compared to GCC's implementation. And what's the benefits of having smaller types? Any ideas?
Better case locality.
Right, exactly. So, well, the user benefit, we got smaller memory footprints and we got better cache locality. And I have one more observation, because stood expected is a type that is likely to be used as a return type of a function. So imagine we have this function, compute, which returns as stood expected, right? And for simplicity, my function only returns, just create a value full inside. And with GCC's implementation, that's basically the code generation. Thanks to the return value optimization, GCC directly put the value inside the caller's stack. However, you still need some code to manage the stack pointer. That's what it is, it's managing the stack pointer. And with our implementation in this particular case, because our stood expected is only 8 bytes, it is smaller enough to fit into a register. So the compiler directly writes the result into the return value register RAX. So that's how we can get some benefit of having smallish types. So the takeaway of this example I'd like to share is that you can use this attribute, no unique address, to reuse the tail paddings inside your class. So that also includes the tail padding of an empty type, because an empty type naturally has 1 byte tail padding. That's the rule of C++. And traditionally, we've been using empty-based optimization, and now we can use no unique address. So let me move on to our next example. Still stood expected, still with no unique address. And this is an actual bug we shipped in libc for one release. And the bug is inside this copy constructor. So in this copy constructor of expected, we first initialize the Boolean hash value from the other expected. Makes sense, right? And then if hash value is true, we got a value, we're going to call the copy constructor of the value. The stood constructor will eventually call placement new and invoke the copy constructor. And if we don't have that value, we call the copy constructor of the error. So looks very simple and reasonable. However, things are not always simple. I will show you the bug report we have. So this is the user's code. They create an expected with a value foo, right? And they call the copy constructor to create another one. And they check the copy hash value should be true, which makes sense. However, due to the bug, it's false. So why is that? Any guess? Exactly. So this is the bug boils down to the rule of C++ zero initializations rule. So the standard says during zero initialization, all the padding bits are zeroed. And this is what happened exactly. We first initialize our Boolean, which is true in this case. And then we call the copy constructor of the foo at the memory address of inside our union, right? And eventually it will do a zero initialization. And because our Boolean lives inside the tail padding, inside the padding, it's got zeroed out. And that's why we got this bug. And to fix this particular bug, we have to initialize this Boolean after we invoke the constructor, invoke the initialization of the foo, the value or the error. But the takeaway from this example I'd like to share is that no unique address is great, and you can use it safely in most of the cases to make your memory more compact. However, don't mix it with manual lifetime management like union or construct at or placement new. Otherwise, you run into the possibility of a memory got overwritten. Right. Any questions before I move on to the next example? Yes?
So let's say like full type has like an assignment operator that use main copy, like when you try to assign the override padding.
Well, mem copy, you can decide how many bytes you mem copy, right?
The full type does not know that it needs to be used in the unit address as a non-unit address member, right? So
Yes.
in this implementation, it can make main copy including the tail because you access.
Yes, that's a very very good question, and I would say it's a very dangerous implementation of an assignment if you just do mem copy, because you might run into cases like this. But that falls into the same takeaway. I conclude that as a manual lifetime management. You use mem copy unless you really know what you are doing. Right.
You must be careful what time you actually dismiss.
Well, we don't actually care about that. The user needs to. It will work for most of the type unless the user has a really weird implementation like do mem copy, which is really dangerous, right? So the next example is about stop token. So these three classes were added in CppCon 20. They are used for concurrency. They are concurrency utilities. And basically, this slide shows an example how you can use it. So on thread 1, you can ask the stop source to register a stop token, to get a stop token. Then you can periodically query the stop requested flag from the token. So if stop is not requested, you can do some work. Otherwise, you exit, then do some cleanup, right? And on thread 2 and 3, you can register as many as stop callbacks as possible. They are callbacks. And on another different thread, at a certain time, you can say, stop source request stop. And what happened when you call that function is that it will set the stop request flag. So thread 1, that while loop will exit and do some cleanup. And the stop callbacks you registered on the thread 2 and thread 3 will be sequentially evaluated on the thread 4. Right. So now let's think about how we can implement these three classes. From what we can see that all these threads, all these classes, they somehow communicate with each other. And a simple way to achieve this is under the hood. We can have a stop state, a shared state. And all the stop source, stop token, stop callbacks, they hold a shared pointer to this shared state, and they can mutate and inform each other. But how do we design this shared state? And let's go back and to look at the requirements we need to have. So we need to implement lots of functions. The first one is we need to implement this stop requested function. And to implement that function, we need sort of a flag to tell us if it is requested. And there's another function we need to implement, which is called stop possible. So the way it works is that if all the stop sources are destroyed, then nobody can make a stop request anymore. Then stop possible should return false, right? But to implement this function, we need to keep track of number of live stop sources. And for the stop callbacks, as I said, we need to sequentially evaluate the callbacks. So we need to somehow store a list to the reference of all the callbacks so we can iterate through them. And then because this is about concurrency, so we can't have a normal list. We need to synchronize this list with some sort of synchronization. However, I can't really use a vanilla mutex because mutex locking and unlocking can throw exception. And all these functions are required to be no except. So we can probably try catch and a while loop, for example, but we can't directly use a mutex. And lastly, because this is a shared state, we need to manage its own lifetime. So as shown in the previous slides, we can use a shared pointer, for example. And this is how a naive implementation looks like. First, we need an atomic Boolean, right, to indicate that flag. And then we can have an atomic integer. And that atomic integer is count number of stop sources. and to implement this stop possible function. And for the stop callbacks, or naively, we can use a std list of the callback pointers. And lastly, we can have a mutex to guard against this list. We probably need to try catch and do some stuff. And with this naive implementation, the stop state is 72 bytes in libc, and plus additional memory allocation for each node in the std list, right? And for the stop token, because I said we need a shared pointer, and a shared pointer is 16 bytes, because you need a pointer to the control block and a pointer to your object. So that's a lot of memory. I mean, which is not very efficient, memory efficient. And maybe let's look at how we implement this shared state. We first have a 32-bit integer, atomic integer, but we use this atomic integer for multiple purposes. Right. So and for the lowest bit, we use it as a stop requested bit. At the end of the day, we don't need a bool. A bool is a byte, but we don't need a byte to store as flag. We just need a bit, right? And for the second bit, we use it as callback list locked, so we don't need a mutex. And thanks to the CppCon addition to the atomic API, now we can implement a unique lock with atomic wait, atomic notify, and compare exchange loop. So you just need one bit with all these operations to effectively implement a mutex or a unique lock, right? And for the rest 30-bit in this integer, we use it as stop source counter. That's for the stop possible function. And now for the stop callback. Because we don't really own these callbacks, the actual user who creates them owns them. So we don't need a std list to allocate all the memory. And in libc, we have a very lightweight thing called intrusive list view. So it is just a lightweight view on the list. And under the hood, it will just store a pointer to the root node. And each node will store a pointer to the previous and next node. Right? And for this lightweight class, it only holds a pointer to the root node. And if we look at this class, we got a 4-byte integer at the beginning and an 8-byte integer, 8-byte pointer at the end. And what you can notice, there is a hole in the middle. What is that? That's the padding. So if you have a 4-byte integer and an 8-byte pointer, you will have a 4-byte padding in the middle of your class, which is a waste of memory. And we happen to fit another 4-byte integer in the middle. We don't really need a shared pointer because we don't need a control block, we don't need a weak pointer, because all we need is to manage the lifetime of this class itself. So we can just have a reference counting for the stop token, stop callback, and stop sources, right? And with this reference counting inside this class, we no longer need a shared pointer because we can use something. Well, in libc, we have a thing called intrusive shared pointer, which is just a shared pointer without the control block. It will, because we store the reference counting inside the class itself. So with this implementation, the stop state is only 16 bytes compared to the 72 bytes of the previous naive implementation. And for the stop token, it's down to 8 bytes because we don't need the share pointer anymore. We don't need the pointer to the control block. So we just need a intrusive share pointer to the object itself. And the takeaway of this example I'd like to share is that sometimes we can try to reuse unused bits to save some space. In this example, we use a 32-bit integer for 3 different like objects, not objects, but like 3 different purposes. And the second takeaway is that when you design your class, you can look for some hole inside your class. You might have lots of paddings in the middle of your class, and that's a place where you can fit something else for free storage. Right. Before I move to the next example, do you have any questions? Okay, please.
Now you mentioned that stop callback has to be no except, right?
Yes.
But you have to do memory allocation, so how does that to be no except?
The evaluation has to be no except, like the registration and deregistration, but we only allocate the stop state when we first create the stop source.
But you also have to allocate the not to stop.
Use the microphone, please.
So you have to allocate the node to store the callback, right, to link it into the intrusive linked list.
Right. The node itself is actually stop callback. Stop callback itself is a node. So the user who creates the callback, they probably are created on the stack, right?
Oh, on the stack.
Yeah, they're probably going to create on the stack. So the node is on the stack, right? So the intrusive intrusive list is not allocating for nodes. The node is the stop callback.
Oh, I see.
Right. Cool. So now I'm going to move the topic to algorithms. And the algorithm I'd like to talk first is for each, the simplest ever algorithm. Imagine I have a std deck, right? And all I want to do is I want to iterate through all the elements and then modify each of the int to apply a cap and a floor, just clamp it. And the first way of doing this is I write a range for loop and call std clamp to modify it on the fly. And the second way I'm doing this, I'm using this ranges for each, and with exactly the same thing. Do you think there will be any performance difference? Hands up if you think the performance should be exactly the same, these 2 versions. Hands up if you think the second one will be faster. Right, have a few. Okay, so that's the benchmark. We can see with ranges for each version, it's between 3 times to 12 times faster. How is that even possible? Like ranges for each is just a for loop, right? And let's take a step back and look at what std_dec is. A std_dec contains a number of memory blocks, and each memory block is a fixed size contiguous memory. And the std block will have an array of block pointers pointing to the beginning of each memory block. And like if you can think of std_dec as an array of arrays. And now if you write the ranged for loop, because the C-purpose iteration model is based on iterators. So, well, this is not exactly what the compiler would generate, but that's the simplified version. What the compiler would generate if you write a ranged for loop. It would say, you call begin, and it will write a traditional for loop with incrementing your iterator. And our dec iterator looks like this. Well, the operator plus plus. Something like that. We're going to increment the element pointer, and if that pointer reaches the end of the block, and we're going to increment the block iterator, then reset the element iterator to the beginning of the next block, right? So that's not super complicated, but it's complicated enough for the compiler to understand the whole picture and to do any optimization on it. And let's look at our library solution. So first of all, there is this segmented iterator concept coming from this paper. And we introduced this concept into libc++. So segmented iterators are iterators over ranges of subranges. Like our dec iterator is exactly one of these, is a range of subranges. And if we perform optimizations on segmented iterator, we can allow algorithms to operate on the subranges more natively. So how does that work? Let me show you this helper function first. This is the key of the optimization for each segment. So first of all, if you pass to a range like a begin and end iterator that models the segmented iterator concept, we're going to first ask the trace, can you unwrap this iterator and give me the outer iterator? And then we're going to write a for loop to iterate through this outer iterator. So in the deck case, this will be a loop over the memory blocks. And for each block, we're going to ask the trace again, can you unwrap the iterator and give me the inner iterator? So the inner iterator in this case is for each block is the element iterator. And now for ranges for each, and we have an optimization. If your inputs model this concept, well, this morning I think most of you attend the generic programming and concept talk. And we are like a concrete example in the library. We optimize based on concept. If your input models the concept, we're going to call this helper function, and which we're going to write an outer for loop. And for the inner loop, we're going to call std for each again, but on the inner iterator type. So if you look at these two blocks of code together, all we did was to rewrite a flattened ranges for each into a nested for loop. And the key thing here is the inner loop iterator type. The inner loop, inner block is a contiguous block, memory block. And the iterator type is just a row pointer. And the compiler is really good at optimizing for loop with row pointers. And if we look at the code generation, on the right-hand side, it is the range for each version. You can see the compiler generates lots of SIMD instructions with these XMM wide registers. And what it does is essentially it vectorizes the inner loop. That's why we get a lot more faster with the ranges for each version. Okay. So let me move on to the next algorithm, ranges copy. And in this case, we don't have a deck anymore. We have a vector of a vector of int, like a nested vector as an input. And all I want to do is I want to copy every single element of this int into my out vector. And there are two ways. Well, a natural way, you would write a nested for loop like this and keep calling pushback with a reserve, of course. And because in this case, our inner loop is iterating over a vector, so it's already contiguous. So our compiler can already vectorize this operation. So in theory, it should get an optimal performance already. And the second way is we use ranges copy. And because our input is not really a sequence of ints, it's a nested structure, we have to use this reviews join, which is a cppus 20 ranges adapter, which will provide you a flattened view of a nested ranges. And then we can call ranges copy on this flattened view and copy all the elements into the out vector. So hands up if you think they should perform exactly the same, the performance. Hands up if you think the ranges copy is faster. Right. Yes, so this is the benchmark. You can see the ranges copy is still 50% to 5 times faster, even though the for loop version should already be vectorized. And this is the optimization we've been doing. So first of all, join view iterator is naturally a segmented iterator because join view is naturally a range of subranges. So its iterator will model this concept. It will benefit from the same optimization we've been doing. And for the ranges for each algorithm, if the inputs model this concept, we're going to reuse that for each segment, which is going to unwrap the iterator and write out us the outer for loop. Right? And for the inner loop, we're going to delegate to the ranges copy again. So we recursively call ranges copy, but the type will be the inner iterator type because the concept or the algorithm already unwraps the iterator to the inner iterator. In this case, will be the vector int iterator. And it happens that we have an existing optimization on ranges copy. So there's an existing optimization. If your input is contiguous, and if your element type is trivially copyable, we can lower the operation copying the whole range into a mem move or mem copy. So this implementation is this optimization because our inner ranges copy is operating on a vector int, which will satisfy this constraints. So it will reuse this optimization. So if we put these two blocks together, the segmented iterator concept help us to unwrap the iterator to the vector int, and the second case is an existing optimization which can be used because the iterator is already unwrapped. And that is why we gain performance, because the inner loop is effectively a mem move. So the takeaway of these two examples I'd like to share is that we constantly add optimizations to algorithms. Please do use them. And we do optimization based on concept. We don't just pick a type and say, yeah, we do it. We trying to categorize them, trying to do generic programming on the concept, which is exactly what Bjorn was talking about this morning. And our optimization are often generic and composable. So in this case, we can see we managed to reuse an existing optimization without any more work. So any question before I move on again? Okay, please.
Have you tried generalizing this to what people call tensors? So in your case, you go for one-dimensional vector essentially the matrix.
We need questions on the microphone or the recording won't get them.
All right. Yeah.
Have you tried generalizing this to what people call tensors? So n-ary arrays, instead of what you essentially have like a two-dimensional array?
Yes.
I'm just curious, with tensors now being so prevalent, or n-ary arrays or whatever,
Right.
do you see the same improvements in performance?
Well, because
And even
tensors.
the algo, could you essentially have inductive recursive step? You had the while loop there.
Mhm.
Can you do this recursively, basically?
Yeah, it is recursive, but there needs to be some optim mechanism because we do optimization only for the standard library. The tensors is not part of the standard library.
But have you sort of like empirically just tried with, let's say, three dimensions?
In theory, if ND array is adopted, we will definitely, as iterator type, will model this concept. It will definitely benefit from the optimization. But ND array is still not in the standard yet. There's MD span, which will potentially
Improve things a little.
yeah. Thank you. Okay, now I'm going to move the topic to containers. So the container I'd like to talk about is FlatMap. FlatMap is a container adapter added in CppCon 23. It provides the same interface as a standard map, but the difference is that under the hood, instead of storing a tree, it stores two sequence containers. So I'm going to give you an example. If there's a flat map from int to double, under the hood, there will be a vector of int to store the keys and a vector of double to store the values. And we keep the keys always sorted so that we can have log n time lookup, right? And now, well, by the way, there's no unique address everywhere. Basically, no unique address is everywhere in our Libc purpose implementation. Anywhere anything can have tail paddings or empty. No unique address will be helpful to reuse any tail paddings. Imagine we have two flat map, M1 and M2. And all I want to do is I want to insert every single element from M2 into M1. And the naive way of writing this code is you write a for loop, and then you in-place every single key value pairs into the first one. Any problem with this for loop? Right. So the problem is about time complexity. As I mentioned, we need to keep this vector always sorted. So every insertion, it will do a binary search to find the right place and insert it there. And because it's a vector, it needs to shift all the elements to the right, further to the right. So every insertion is a linear, right? Makes sense. And because this is a for loop, so overall it's got quadratic complexity, which is really bad. And luckily, standard provides a different API called insert range. So if you want to insert a whole range of pairs, key value pairs, and the standard says with this function you can get m plus m log m time complexity to insert the whole range. And now what you can do is you can do m1.insert range m2. And that will give you a m log m plus n complexity instead of a quadratic function, which is much better. And even better, there's another overload. If you know your inputs are already sorted, you can tell the library, pass this tag type sorted unique, and to tell the library my inputs are already sorted. And the library will skip the sorting step, so you get a linear complexity. And in this case, you can just do m1 insert range sorted unique m2. But now the question is, as a library vendor, how do we implement these insert ranges? So in a nutshell, this is not exactly how we implement it. So there are a couple of steps to insert range. As I mentioned, we have a vector of keys and vector values. So the first step is we append all the new elements at the end of the two vectors, right? Then we partially sort the newly inserted elements, right? So after this step, we're going to have two sorted subranges inside our vector. By the way, for the sorted unique overload, this step can be skipped. And then we can in place merge two sorted ranges into a single sorted range, sorted vector. And then we can remove the duplicates at the end. There might be some optimization you can do to combine the last two steps, the merge and remove duplicates in the one pass. But the thing I'd like to talk about is for the simple thing. How do we append the new range at the end of the vector? It sounds quite easy. So this is the most generic implementation. Right? All you do, you write a for loop. You're given a range of pair-like things. You just write a for loop, and you get a pair out of each element. And then you insert pair.first at the end of the key vector and pair.second at the end of the value vector. Well, this works, so because it's most generic way of implementing this function, but it inserts one element at a time. And we're going to miss some optimizations on a vector insert with the ranged version. So vector insert has another overload where you pass a position and a pair of iterator, and it's going to insert a whole range of elements. And we have lots of optimizations on this overload. For example, if your inputs are contiguous and the type elements are trivially copyable, we're going to just do a mem copy to copy the whole range. And ideally, we can use this overload and to benefit from our existing optimization. But the element types are not the same. We're given a range of pairs, but we got vector of ints and vector doubles. Their elements type don't really match. And we can't really use that overload. However, because we're inserting one flat map into another flat map, even though flat map presented us a range of pairs, but we know that under the hood, flat map has a key vector and a value vector. So at the end of the day, we're just inserting two vectors into another two vectors. So in theory, we should be able to use this vector insert. We just need to do some clever things in the library. And to solve this problem, we introduced another concept called product iterator. Product iterators are iterators that aggregate multiple underlying iterators. And flat map iterator is naturally a product iterator because it aggregates the key vectors iterator and the value vector iterator, right? And because we have this concept, we can write an optimization based on this concept. If your inputs happen to model this product iterator concept, what we can do is that we can ask the trace, can you unwrap this product iterator and give me the underlying zeros iterator and ones iterator? I mean, by zeros and ones, I mean, because flat map iterator has two iterators. So with this technique, the trace will unwrap the flat map iterator into a vector, key vector iterator and value vector iterator. Then we can call that overload the ranged overload. And with this overload, we're going to benefit from the existing optimization where we can mem copy the whole thing into the vector. And we can do the same for the values vector, right? And thanks to this optimization, we gain about 2 to 10 times performance gain just to unwrap this iterator, right? Thanks to the existing optimization as well, because yeah, that's what's worked. Like the mem copy is the key thing that makes it faster. So the second example is slightly different. Now I don't have a second flat map. I have a vector of int for the new keys and a vector of double for the new values. And now instead of inserting the second flat map into the first one, I'd like to insert all the new keys and new values into my flat map. How would you do it? Well, don't use a for loop, that's quadratic. So to use insert range, you need to have a range of pair-like things. But here we don't have pairs, we have vectors, ints and vector doubles. And in CppCon, we have another range adapter called viewZip. So with this viewZip, it can zip multiple ranges into a single range that provides a tuple or pair-like elements. So what you can do here, you can just say m.insert range viewZip new keys, new values. And because zip view iterator is naturally a product iterator, because zip view naturally zip multiple ranges, and zip view iterator naturally aggregates multiple iterators. And because it models the concept, you benefit from the same optimization of the insert range, and you will get the same optimization and same performance speed up. And that's also echoes Beyond's point of generic programming. You do generic programming based on concepts. So the key message I'd like to share here is when you use standard library or containers, try to use the most precise API. So when you would like to insert a range of elements, there's an insert range. You don't roll your own for loop. And if you know your inputs are already sorted, you can pass the sorted unique tag so the library can skip the sorting step. And also try to use the library facilities like viewZip instead of roll your own zipping mechanism or write a like lockstep for loop or whatever. Because if you use library facilities, you're going to benefit from the library optimization, concept-based optimizations. Okay. Before I move on to the next example, do you have any questions? Right. Okay. So now I'm going to move the topic into testing. Testing standard library is quite different from testing application code. Because the standard library implementation is, we have a very, very, very clear spec, that is a standard spec. And there's very clear requirements. And also the risk of having a bug is too high. We cannot change our ABI. We have to maintain our ABI stability. And sometimes if you have a bug, and if you need an ABI break to fix a bug, we might opt to just live with the bug forever, because changing the ABI cost is way higher than just having a small impact bug. And that's why we test almost every single word in the standard. I'm going to show you an example. That's a snippet of text I copy-pasted from the standard. This is the move constructor of the stood expected. And it got lots of text underneath and a declaration on the top. What do you think, as a library implementer, what do you think we should test? Any suggestions? Constraint, exactly. We need to test when the constraint fails, the function should be finished away. As I said, we test every single word in the standard. So for example, the first word is const_exp. We need to make sure this function works in the const_exp context. And this is a move constructor. Because it's a constructor, the absence of the explicit keyword is also tested. And there's a no-except specification. We need to make sure the no-except specification matches the standard. So when the condition match, then it is no-except. Otherwise, it can throw. We got effects, we got post conditions, we got exception specifications. Everything needs to be tested. I'm going to show you the first example about how we test const_exp. So the way we write test for const_exp is very simple. We just write a const_exp function which returns a Boolean. And we're gonna just write our normal test points. So like what you do in your normal unit test, you exercise your function. In this case, we exercise the move constructor. Then we check the results are expected. And we're using vanilla assert macro because this macro is blessed. In the const_exp context, assert macro is only a constant expression, only if the thing inside the parentheses is true. So if the thing inside it is false, it will generate a non-constant expression, then the compiler will complain if you use this function in a const_exp context. And then in the main function, we just run the test like a normal function. So that's how we run the usual runtime test. And then we call static assert with the same test. So that will run the test in the const_exp interpreter. So this way, we can share the same test between the compile time and the runtime. So you don't need to write separate function testing unit tests for your const_exp implementation. You just use the same tests. And now let's talk about testing constraints. Constraints is keyword in the standard. It can translate to requires. So for example, this is a move constructor. There's a constraint that the underlying type needs to be move constructible. So if there is a violation in the constraints, the implementation should finish out this function. So this function should be wiped out. And to test that is quite simple. You just write some negative case. So I write a foo which is not move constructible. And then you can just write some static assert. You either with some concepts, helper concepts. So you can So all we need to test is to test that when this is violated, this expected move constructor doesn't exist, right? The way you test it, you either write a concept saying move constructor exists, then your extraction is a move constructor, or there's already a standard trace called is move constructible. So in this case, we can just use that trace to test that this expected function no longer exists when it is violated. And for testing mandates, the mandates keywords is slightly different from the constraints keywords. So the mandates keyword means that if a violation in the mandates is guaranteed to generate a diagnostic from the compiler. So the mandates translates to static assert. Right. So if we violate this constraint, this mandates, the function still exists, but if you call it, you get a static assert failure. Does that make any sense? Right? So to test static assert is very different. We can't use concept to check the existence of the function because the function always exists. And we effectively need to test that if you write some code that violates the mandates, we should test that this code should not compile. And this is not something we usually do in an application code, right? So only in the library implementation, we need to test. Well, we need to emit static assert at the right place with the right error messages. And the way we test that is that we write some code that doesn't compile, shouldn't compile, and we write a comment with some keyword, expected error RE or something, with a regular expression of that expected compiler error messages. And clan has some magic. We can pass some compiler flag to clan and says -clan -verify. What clan would do is that it will try to compile this code and it will match the compiler error messages with your regular expression. If you match, compiler is happy. If it doesn't match, compiler will emit errors. So that's how we test static assert in the standard library. And now for the preconditions. And precondition violations in the standard is pure undefined behavior. So if a user writes some code that violates a precondition of a standard library function, it's up to the user. The user can get anything, like can crash or do some random stuff. But as library implementer, we would like to help the user to diagnose the error in some debug build or some other build. So preconditions or hardened preconditions translates to assert or contract assert. Some of you might have attended help Sutter's talk about contracts. So contract assert is one use case is for preconditions, or some other assert macros, or some pre or post. And to help the user to diagnostic the error. So if the user happen to debug build their program and they will see some assertion failure instead of some random error messages. So the way we tested our own assertion is that, well, we can't really test it nicely. We need to test, because it's purely runtime, we need to test some code that violates the preconditions that will emit an assertion failure and break down your program as expected. And the way we test it, we have another macro, test libcpp assert failure, with an expression and expected error messages. So what this macro does under the hood is that it will install the assertion handler, and then it will fork the process, and then it will let the child process to run this expression to fail and trigger the assertion. And then we check the standard error of that child process, and then we match the error message with that child process. So that's how we test assertion failures. So the takeaway of this testing is that we share the test from the compiler time test and runtime test with a simple const export function. And we use negative tests to ensure things are failed as expected. Right, so if something fails, we don't just fail. We need to make sure that it fails in the expected way. Produce either a static assertion compiler of error messages or a runtime assertion failure. And lastly, this compiler flag is very useful to test static assert. Cool. So I pasted, if you're interested to contribute to Libc purpose, it's an open source project, and we have a clear documentation about how you can contribute. And we also have a GitHub issue link where you can see all our existing bugs or unimplemented papers or issues, and you can start to pick some simple ones. And lastly, QRT is a hedge fund in London, and we are constantly hiring. We've been using C purpose extensively in the house, and if you're interested, you can check our website or talk to me. And yeah, so that concludes my talk. Any questions? Yes, please. Yeah.
Great talk. This may be a silly question, but when would the same test fail at runtime, say, but pass in the context or context?
Yeah.
Like with the same inputs. When would that happen?
Because sometimes we have a different code path in a const export code path.
Okay.
If you're aware, there's an if const eval.
Yeah.
And we've been doing that a lot because there are lots of things we can't do at compile time. For example, for type erasure, we usually allocate a memory for chars and reinterpret cast into some object, which is not allowed in a const export time.
Okay.
So there are different code paths.
Yeah.
So it's possible.
Okay. Thanks.
Cool. Yes, please.
So, do you have any testing process for API compatibility?
We actually do, but it's not thoroughly. We have a list of symbols we export, and we just make sure all the symbols are the same. Yeah.
Do you test for like argument type, return type, or anything, or like just rely on human code review?
Well, we have, not really. I mean, we have a concrete unit test, like with a list of symbols. We make sure the dynamic library contains these symbols, exact same symbols. And also, most of our library implementation are header only, 90%. So they're mostly in a header. And we have some ABI tag to tag every single function. So every release, each function will have a different symbol name. So that's how we work around ABI issues.
Thank you.
No problem. Cool.
Something like this was asked earlier, but how easy is it to integrate with that optimization for segmented iterators? If I have a vector of std array, for example,
Yes.
will I get, oh, I'm sorry, I think you already answered this when you talked about a vector of vectors.
Yes.
Okay. Suppose I have a custom type
Yes.
that is like a vector.
Yes. Yes. So our concept is a bit there's a opt-in mechanism. So unfortunately, that is you can like if you need to implement some trace to tell the trace how to unwrap your iterator. But however, these traces are double underscore prefixed. So it's like a library implementation detail name. You wouldn't know that.
Okay.
So in theory, you can implement our trace for your own type. That you would benefit from the same optimization, but that name is start with double underscore. So it's up, like, for one, you don't know that name. Two, it's undefined behavior to use name with double underscore.
All right. So if it happens to be like a vector of arrays, you can maybe expose it as a span of arrays, and then I would get the same benefits because it's still a span of still arrays.
Yeah, I mean, if it is standard library type, it will likely get the same optimization. No problem. All right, I think no more questions. Thank you very much for your time.